We went through an example of simplified DES last week. We didn't complete the entire encryption, but we went through one round, and you, as your homework over the last few days, have finished the other round. And two things, or we need one thing that's not given in the lecture notes that you needed to work out was the inverse of the initial permutation, so we'll talk about that. And we'll talk about the remaining steps, that is the decryption. So basically what we did was, in this diagram, the initial permutation, the function f of k, and we swapped the halves. That's where we got to. Let's get a pointer. So we start with plain text, initial permutation, and then the function f of k. This block here is in fact a very complex set of steps, which, where is it? One of these more detailed diagrams. This dark grey box here is f of k. We see f of k here as the input is the output of initial permutation, and the output of f of k goes into the box that swaps the halves or switches the halves. So there are multiple steps, including the S boxes in there. We got to here, we then swapped the halves, the left and right half, and then you repeat those operations, but of course you have different input and a different key. We used the round key K2, but all the operations are the same. Same expand and permutate, XOR, the same two S boxes are used, and a P4, the permutation, and then we get an output. So we have 8 bits output there. 4 bits come from the input, the right-hand side, and the other 4 bits come from applying this. We see a uppercase F, which is this light grey box in here, if we look at that as a function as well. We get 8 bits output, and then we apply an inverse permutation, or an inverse of the initial permutation, which is the inverse of this first step, and we get the ciphertext as output. So the one question is, what is the inverse of the initial permutation? And we define on, here it is, on this slide, the initial permutation. What's the inverse? Anyone tell me? I'll write down what IP is. It rearranges to 2, 6, 3, 1, 4, 8, 5, 7. What's the inverse of that operation? Either an explanation or what is the exact inverse? Map from the output to the input in what? Okay. I don't know if that makes sense. The inverse is the operation such that after applying the inverse, the output will be the same as this input. We take some input into IP and we get some output. Let's say some bits A go in to the initial permutation, we get some output B. If we apply the inverse, the output should be A again. That is, take some bits, apply the initial permutation, apply the inverse of that, and we should get the exact same bits out here. That's the idea there. Good morning. So This defines the rearrangement of the bits. We take bit 1 and it moves to the 4th position. Bit 2 moves to the 1st position, and so on. That's IP. What rearrangement is such that the bits that come in will be here, will come out of the IP inverse.
So send back to the original position?
Yes, send back to the original position. So what is the definition then? 1,4. How would we? Okay. It's an 8. If we write down the inverse of IP, the original first bit at the start moved to the 4th position after IP. We need to move it back to the 1st position after the inverse. It's the first bit moved to the 4th position, therefore we want to move the 4th bit back to the 1st position. Therefore, if we take bit 4 and it becomes the 1st bit at the output of IP inverse. Next one. Bit 2 moves to position 1 when we apply the initial permutation. So bit 1 needs to move to position 2. So we get 1 there. Next one's the easiest one. 3 doesn't move. 4 is in the 5th position. It needs to move to the 4th position. So what have we got? 5. 5 is in the 7th position. So the 7th bit needs to move to the here, the 5th position. Some people are getting it, that's okay. Let's make sure everyone gets it. What we want to do is rearrange our bits such that if we apply the initial permutation and then apply the inverse of that, then the input to the initial permutation is the same as the output of our inverse initial permutation. That is, get the bits back in the right order. Start 1, 2, 3, 4, 5, 6, 7, 8. Apply this. Bit 1 moves to the 4th position. By applying the inverse, we need to move the 4th bit to the 1st position. So bit 4 moves to position 1. So what's the bit in position 6? Work out the last 3 and write them on a piece of paper. What are they?
1, 2, 3.
286. Is that correct? Bit 6 moved to the second position. Therefore, the second bit needs to move to the 6th position. Here. 2 moves to 6. 7 becomes 8. Therefore, the 8th bit moves to the 7th bit. And we have 1 remaining. That's the definition of the inverse IP. Once you work that out, then you can complete your encryption and find the ciphertext with simplified DES for our example from last week. And when you found the ciphertext, in fact, I think in the lecture notes I gave you the ciphertext, the plain text, the key and the ciphertext. When you find that, you can, in any case, any example, you can check whether the ciphertext you got is correct, or at least a high chance that you made no mistakes, by decrypting the ciphertext and getting the original plaintext back. Of course, it takes a lot of time, but the steps are the same. Look at the decryption process. Initial permutation, same as encryption. F of k, it's the same block as here. Those steps of expand and permutate, S boxes and so on. Swap the halves. F of k, inverse initial permutation. Decryption is identical to encryption in simplified DES and in real DES. That is, same steps. If I asked you to implement in C code for your next assignment or homework, both encryption and decryption, then you only need to implement one because they do the same. It's just the inputs differ. The inputs, of course, we take our ciphertext as input and we use the round keys in the opposite order. Same round keys, K1 and K2, but we use K2 in the first round and K1 in the second round in the decryption. That's the only difference there. Any questions about simplified DES or the initial permutation before we move on and look at some of the design characteristics? You got it wrong. The encryption.
After input to IP inverse something else. So this is the correct answer.
Yes, in the lecture notes on slide 24, the correct ciphertext is given as what you should get.
No, didn't get it.
This is the example we went through in the lecture. We started with this plain text, with this key. We got halfway through after round 1. You completed and you should have got this ciphertext.
And how about this to...
We've covered these two. LS1 is left shift by 1 position. LS2 is left shift by 2 positions. Just shift a bit left, but wrap around. We did those steps in our key generation. If you remember back, the first thing we do is we generate our round keys. We take our 10-bit key and apply these steps. Yep. That was key generation. Encryption, we did this. We got to here. You can finish and get the ciphertext. If you make a mistake, then first attempt, go back and try again. And try again. It's easy to make a mistake on the first few times because it's quite confusing with all those zeros and ones. But the operations themselves are quite simple. The main point is to demonstrate the different operations that are used. note that our substitution boxes that we use, the S boxes, were perhaps the most complex part of the cipher and contribute to the confusion for the relating the input plaintext key to the ciphertext. So our principles of diffusion and confusion, the S boxes contribute to the confusion. We'll come back and see the principles of the design in a moment. We took 4 bits as input. Those 4 bits determined the row and the column, and we got 2 bits out. They are non-linear operations in that there's not a one-to-one mapping between every possible input and every possible output. The 4 bits, or the inputs, we have many or multiple possible outputs, for example, of 0, 1 here, 0, 1 here, 0, 1, 0, 1. So with 2 different inputs, we could get the same output. That is, if our input was 0, 0, 0, 0, we'd get 0, 1 as output. If our input pointed to this element, we'd get 0, 1 as output. 2 different inputs produce the same output in this. It's a non-linear operation, and that's needed for the security of the system. If it was a linear operation, it would be much easier to attack. So, simplified DES is just for education. It's not used in real life. We could express the operations as a set of mathematical functions or equations, where the ciphertext, we take our plaintext, we apply the initial permutation, apply some function f with key k1, apply the function that swaps the halves, and then the same function f but with key k2, and then eventually the inverse initial permutation, and the output is the ciphertext. So we could, if we define what those functions are, then that describes the encryption step. And similar for the decryption, and you notice they're the same. The only difference between the encrypt and decrypt function is the order in which the keys are used. Is it secure? Well, we have a 10-bit key. Brute force is easy. It's not secure from that perspective. What about if you could not do a brute force attack, or we don't try a brute force attack, if you know the plaintext and a corresponding ciphertext, can you find the key? And although it's possible, it turns out that it's not straightforward. It's very hard. That is, the operations, the principles used are secure. It's just that we've reduced the size of the cipher. That is, we only have 2 rounds, we have smaller inputs to make it manageable. But the principles used are secure, or considered secure. That is, if I give you in an exam the plaintext, I give you the ciphertext, and I give you the entire algorithm and ask you to find the key, you will not be able to solve it within the 3 hours of the exam. With a computer, okay, you'd need to write some software to do that. But the principles are considered secure. What about comparing now to the real life DES? That's what's used or has been used in the past. The size of all the operations and inputs differ. Here's some comparison. Simplified DES, we had 8-bit blocks, plaintext of 8 bits, ciphertext of 8 bits. Real DES, 64-bit blocks. The larger block size is needed to make frequency analysis attacks harder. With a very small block size, our input plaintext repeats much more than a large block size. So a 64-bit block is typical for most ciphers. 64, 128 bits is typical block size. DES uses a 56-bit key, and it has 16 rounds. Simplified DES had 2 rounds. With 16 rounds, we need 16 round keys. Remember, we generate keys for each round. In simplified DES, we generated 2 round keys of 8 bits. In real DES, we generate 16 round keys of 48 bits in length. So our round key, K1, K2, K16, in DES are 48-bit values. Initial permutation, 64 bits. The function f, which we saw in one of those grey boxes, operates on 32 bits. In our simplified DES, just 4 bits. And we have 8 S boxes instead of the 2 S boxes that we needed for simplified DES. Same principles, same steps, just that the operations we use are larger. Operating on more bits, we have more rounds and so on. Here's an equation for simplified DES encryption. And this is what it looks like for DES encryption. We've hidden some details. Take the plain text, initial permutation, apply our function with key K1 and swap the halves, apply our function with key K2, swap the halves, function with key K3, swap the halves, function with key K15, swap the halves, function with key K16, inverse initial permutation. So it's just expanded to repeat the operations more times, more rounds. But the principles are the same. We're not going to go through in any depth the details of all those operations in the real DES. I've included in the lecture notes just if you want to look at them, just to give an indication of their size and their structure, but we'll just skip through them and look at the design issues. This just shows the encryption algorithm where this is the encryption side and this is the generation of the key. Again, without going into details, we use left shifts, we have multiple rounds. IP, the initial permutation, it's not 8 bits input and rearranged like this. The definition of the initial permutation in DES is shown here. We have 64 bits input and rearrange those bits in this way. That is, the first bit moves, if we read row by row, into this position. The 64th bit moves to this position. So it just defines the rearrangement of those bits and the inverse. And the other permutations are defined as well. And the round function. Take the halves, left and right half, expand and permutate, XOR, S box, permutate, XOR, and we get the output of that function, f of k. S boxes, there are 8 S boxes. Same concept, we take the bits in to tell us the row and the column to look at, and tells us the value of the bits out of the S box. And they should be non-linear. You see there are multiple occurrences of the output values, 6, 6, 6. So there are multiple occurrences of the same output value. With 2 different inputs, we can get the same output in the S box. Therefore, if you have the output value, 6, which input generated that output value? It's not known. If it was a one-to-one mapping, a linear mapping, then if every input produced a unique output, then if we know the output, we know what input was used. And that makes it easier to do analysis. So having a non-linear mapping makes it harder for analysis, because if I'm the attacker and I know the output of my S box was 6, then how do I work out what was the input? It's either the input that produces this 6, or this 6, or this 6. Maybe there's another one around as well. No, 3, and this 6. So there are 4 possible inputs there. I don't know which one. I'd have to try them all. Makes it harder for the analysis. And the other operations used in the real DES. Let's look at the design of DES and see how some of the design choices were made and whether they were good design choices in producing a strong cipher. One way to analyse the cipher is called using the avalanche effect, whether the cipher has this effect on an input plaintext. And this is defined as saying, if we change the key in a small way, what we'd like is that the output ciphertext is changed in a large way. One small change on the input produces a large change on the output, whether it's changing the key on the input or the plaintext. That's the avalanche effect. That is, something small happens at the top. In an avalanche, a small rock falls from the top of the mountain and it knocks more rocks and knocks more rocks, and eventually the whole mountain is falling down. We have an avalanche. We change one bit on the input, it should affect multiple input bits as we perform the encryption, such that many bits on the output have changed. We want that. And it's easy to measure whether it occurs. And it is present in DES, so that's good for security. We'll show these examples. The two examples here are inputs used for DES. They're shown in hexadecimal, so you can convert them back to binary. So the first example, we're going to take two different plaintext values, same key, but two different plaintexts, and plaintext 1 differs from plaintext 2 by 1 bit. 64 bits in, all right, it's shown as hexadecimal here. We convert that to 64 bits and this to 64 bits. You look at that and you'll see that there's just 1 bit in difference. It's because of the first value here. 0 in hexadecimal becomes 0, 0, 0, 0. 1 becomes 0, 0, 0, 1. 1 bit changes between plaintext 1 and 2. When we encrypt this plaintext 1, we get some ciphertext out with DES. If we encrypt plaintext 2, we get some ciphertext out. Those two ciphertext values differ, in this case, by 32 bits. A change of 1 bit on the input produces a large change on the output. That's desirable. Similar, if we don't change the plaintext but change the key. Here's an example. We just have some plaintext on input. We encrypt with one key value, this one, and get some ciphertext. We encrypt the same plaintext with a different key, key 2, which differs from the first key by just 1 bit, and we get some ciphertext. And in this example, the two ciphertext values differ by 30 bits. Again, a single bit change on the input produces a large change on the output. The avalanche effect is present. That's shown, those operations are shown here for the change in plaintext. That is, we're encrypting the plaintext shown in the first row here. This is the input plaintext 1, this is the input plaintext 2. And what this diagram shows in each box shows the output of the round of DES. DES has 16 rounds plus a final inverse initial permutation. This is the output of round 1 when we encrypt plaintext 1. This is the output of round 1 when we encrypt plaintext 2. And this is the number of bits that differ between these two. 1 bit differs. After round 1, still there's only 1 bit difference between the two output values. After round 2, there are 5 bits that differ. After round 3, 18 bits. Round 4, 34 bits. And we continue around 30 bits differ. Remember, our ciphertext and plaintext are 64 bits. On average, we'd like half of the bits to be different. So we aim to have a value around 32, half of 64, which is a good value. If the difference is 32 bits all the time, then that's good. And it turns out with DES, after round 4, the subsequent rounds result in a large difference, which is good. One thing this tells us that if we apply DES but use just one round, it would not be good in terms of the avalanche effect, because after one round, just one bit is changed. If we had DES which used just 2 rounds, still not so good from the perspective of the avalanche effect. Only 5 bits differ on the output. 3 rounds, not so good. 4 rounds, 5 rounds, that's fine, because we've got a large number of bits that change on the output. So from that perspective, having more than 4 rounds in DES is good. It has 16 rounds. Remember, the trade-off is the more rounds, generally the more secure, but the slower it takes to encrypt. The trade-off between security and performance. Do we have one for the key? This is the same concept, but 2 different keys are used. This is the output plaintext. When we change the key, the output of each operation, well, this is the input plaintext, this is the output of round 1, round 2, round 3, and eventually we get to around 32, which is desirable.
32 or 30-bit change, but
yep.
The rest is the same.
Yes, so if you look at, in this case, all right, although it's in hexadecimal, if you look at that, 30 of those bits have changed in the binary.
0 and 1, 0,
Yeah.
0, 0, some place,
Yeah.
0, 0, 1, 1.
Yeah. This one, here we have 3 bits of change. That is, between the 2 output ciphertext values, you convert this to binary, you can almost see it in hexadecimal. Most of these values are the same. The B and the 9 are different, the 2 and the 6 are different, and the C and the 4 are different. So the number of bits that differ in this case is just 3. Here we have 11 bits differ. It just shows it in hexadecimal because it's harder to write all 64 bits on the slide in the diagram. So the avalanche effect says, yeah, which is desirable for good security, the avalanche effect, a small change on the input key or the input plaintext should lead to a large change on the output ciphertext. If that's present, then that's a good property. And it is present in DES. What else about DES? So it has the avalanche effect, that's good. The key size. In fact, with DES, you start with a 64-bit key, except only 56 bits are used when the key generation step. The other 8 bits are used just for a parity check. So that if you transfer the key to someone, 8 bits are just there to check that you've received the right key to do an error detection. They're not used for the encryption. So from the perspective of an attacker, there are 56 bits that they need to guess. Means a maximum of 2 to the 56, or a key space of 2 to the 56, maximum number of keys of 2 to the power of 56. And we gave an example, I think even in the first week, that there are now machines that will break that in a matter of hours. In 1977, there was an estimate that it would cost $20 million to break it in 10 hours. In 1998, a machine was built that could break it. And today, 56-bit keys is considered too short for a brute force attack. So that's a problem with DES. The key is too short. But the algorithm itself is considered strong. It's just the key length is the problem. How do we improve it? Use a larger key. And we'll see shortly that there's triple DES. Use the same algorithm, but use a key which is longer. Apply the algorithm multiple times, 3 times in this case. So the algorithm is considered secure, the key length is not. Sorry? We will go through the concept of double DES and then triple DES shortly and explain why triple DES is used. 3 DES. Yeah. What about attacks, known attacks on DES? There are, or theoretical attacks, there are some known what's called timing attacks. The concept is that when you encrypt something, the hardware takes some time to do every operation. The CPU takes some time to do the permutation, to do the XOR, and so on. Timing attacks try to take advantage of that to try and work out what the plaintext or key is. That is, by measuring how long encrypting this plaintext takes in each step and comparing it to other cases, use that information to try to derive the key or the plaintext. Possible. It's possible on DES and on other ciphers, but there are very easy ways to prevent it or to stop it from happening. So there are no known useful attacks on DES from that perspective. In theory, it's possible. In practice, it's very easy to prevent. There's some different cryptanalysis techniques that have been applied, and they make use of knowledge of existing pairs of plaintext and ciphertext. That is, if the attacker knows plaintext P and the corresponding ciphertext, they don't know the key. They know some plaintext and the corresponding ciphertext that was produced by encrypting that plaintext. That is, they know the pair plaintext ciphertext. If they know multiple pairs, they can use that information to perform an attack. And there are different approaches. A brute force attack of DES takes on average 2 to the 55 operations. That is, you need to apply, you have 2 to the power of 56 keys. On average, you need to make 2 to the power of 55 attempts to find the key, a brute force attack. That's the worst case. With some knowledge of plaintext, ciphertext pairs, people have worked out that they can break DES in 2 to the power of 47 steps, which is less than 2 to the power of 55. But for that attack to work, the attacker needs to know 2 to the power of 47 different plaintext values, which is not very practical. That is, the attacker needs to know a lot of possible plaintext values to perform this attack. 2 to the power of 55, 2 to the power of 47, that's a difference of 8, effectively 8 bits. This will be, 256 times faster than breaking a 2 to the power of 55 brute force attack. But it requires the attacker to know billions, trillions of different plaintext values. And there's similar with another attack. There's a way to form approximations, linear approximations of the cipher, and again, they can break DES, but they need knowledge of 2 to the power of 43 different plaintext values. That is, they need to know, they don't know the key, they need to know P1 and the corresponding ciphertext. The attacker does. They need to know P2 and the corresponding ciphertext, and they need to know P2 to the power of 43 and the corresponding ciphertext. 2 to the power of 40 is 2 to the power of 43 is 8 trillion. 8 by 10 to the power of 12. So they need to know many possible plaintext ciphertext values, and that's very hard to know that. So in theory, there are some attacks. In practice, they're not very useful. So in practice, DES is considered secure except for the key size. The key length of 56 bits is too short. DES was designed by IBM many years ago with input from security agencies in the US, and the design was considered private. That is, only the people who at IBM and the security agencies knew about how it was designed. They made the decisions of using those particular S boxes, using the initial permutation and so on. So there were questions by other people whether the design was secure. Why was it designed in a particular way? Was it designed in a secure way, or was it designed such that there were some attacks that people could use as a backdoor? That is, that someone who knows about the design can break the cipher, but if you don't know about the design, you cannot break it. That's what the people's concern were about DES. But it turns out that still people consider it to be secure. The S boxes were chosen to provide non-linearity, and that were generally considered to be secure. If you change the S box by a small amount, people have shown a small change in one of the S boxes in DES leads to a much weaker cipher, which suggests that the S boxes were chosen to give the strongest level of security possible. So nowadays they're considered secure. That is, the design is good. The S boxes provide increased confusion, whereas the permutations are chosen to increase the diffusion, and it's been shown that that achieves those effects quite well. So, DES, the algorithm is good. The key length is too short. What do? Use a larger key. And we'll look at the approach if we use a larger key, what we can do, and there's an algorithm called triple DES, written as 3 DES. That is commonly used nowadays. It's recommended in government encryption. Triple DES is recommended compared to DES. Uses the same algorithm, but applies it 3 times. That is, you basically encrypt your plain text 3 times using the DES algorithm, but using 3 different keys. So that's considered strong, which we'll talk about. There's another algorithm that was developed, another cipher, Advanced Encryption Standard, AES, and that's commonly used now. If you use security in your wireless LAN and use encryption, then most likely if you're using strong security, you're using AES. It's commonly used in practice now. And there are other block ciphers. We'll list a few of them. We're not going to go through in any other ciphers in the same detail as DES. That was just to illustrate how it works. Let's look at the concept of taking DES and making the key longer. That is, encrypting multiple times with DES and how it may work. The idea with DES, we take some plain text, apply the DES encryption, get some ciphertext. When we use a single key, the key is 64 bits, but in terms of security, only 56 bits are used. So sometimes you'll see it as a 56-bit key, sometimes as a 64-bit key. It is 64 bits in length, but we only use 56 inside the encryption part. So the idea is, with multiple encryptions of using DES, is you take some plain text as input, you encrypt with DES because the algorithm is considered strong. You take some plain text, encrypt with DES, normal DES, with some 64-bit key, you get some output, and then encrypt again. But in the second case, use a different key. of the same length. And you get the ciphertext out. That's the idea of encrypting multiple times with DES, in this case 2 times, or double encryption. From a brute force attack, in this case, a brute force attack, we need to try all 64 bits, or 56 bits actually. That is, we have 2 to the power of 56 possible keys to try. Here, these are also 56. How many possible keys are there? If I choose a 56-bit key here and a different 56-bit key here, effectively I've chosen 112 bits. So now I'm using 56 because that's the amount used in the encryption. With this approach, the concept is that there are 2 to the power of 112 different keys. Therefore, a brute force attack needs to make this number of attempts, or half that, which is 2 to the power of 111. That's not feasible. If you look at how long that would take, it would take thousands of years to break that. Breaking 56 bits is okay, 112 bits, not possible with brute force attack. But it turns out, and we'll go through in detail how it happens, using this approach, there's there's an attack that's possible that means that an attacker doesn't need to make 2 to the power of 112 attempts. In fact, they just need to make about double the number of attempts as normal DES. It turns out that this is not very secure. We'll go through that attack. Therefore, people have developed triple DES. If we call this double DES, triple DES. Take some plain text, encrypt 3 times with DES. And there are some variations on that. It may be encrypt, decrypt, encrypt, but use different keys. Use 3 different keys, so the key length has gone up to what? 168 bits. 3 times 56. And even with the attack that we will see that's possible against double DES, this one's considered secure. So nowadays triple DES is used. In fact, there's some variations of triple DES. Sometimes they just use 2 different keys, key 1, key 2, key 1. In some variations they use 3 different keys, key 1, key 2, key 3. But the process of having 3 blocks avoids or makes it harder to do the attack that's possible against double DES. So let's go through how double DES can be broken. It can be broken with not much more effort than breaking single DES. This is the illustration of the double DES. Take some plain text, encrypt with a DES algorithm with key K1. We get some intermediate output, X. Take that output and encrypt that with the same algorithm, but we're using a different key, key K2, and we get our ciphertext. That's this one. In fact, it's not just for DES. We can apply other ciphers here. It doesn't have to be DES. It can be any other block cipher. Same concept. Decrypt. Take the ciphertext, decrypt with our decryption operation of the cipher. Using key K2, we get the intermediate output X, decrypt that with key K1, and we get our original plain text. That's the idea. It turns out there's a meet in the middle attack that makes it easier to break. Let's illustrate that with an example. The example I'm going to use comes from a midterm exam, I think 2 years ago. This is our cipher, our block cipher. What it shows is that if I have this plain text, 0000, a 4-bit plain text block, so we have a 4-bit block, and I have key 00, a 2-bit key, then the ciphertext will be 1111. If I encrypt the plain text all zeros with key 01, then this will be the ciphertext. If I encrypt the plain text 1010 with key 10, let's see if I can line up, this will be the ciphertext. So it's just a simplification of some block cipher that takes some plain text input of 4 bits, a 2-bit key. With a 2-bit key, there are 4 possible keys and all the possible ciphertext output values. I just chose these randomly just for this example. Let's apply this. So this is an example of a single operation. Imagine this is our simplified DES cipher, very simplified because we have just 2-bit key. If we apply double operation, then we take our plain text, such as 0000, encrypt with key K1. Let's say I choose 00. I will get the output 1111. That would be here. Then I would encrypt that output with another key. Let's say I choose 10. I would take 1111, encrypt with the key 10, and I would get 1010 as an output. So this is our block cipher called A. If we use double A, that is 2 encryptions, then we'd encrypt once with 1 key and then encrypt again with a 2nd key. Let's see how we can break this cipher and how many operations it takes. Scroll down to our question. Actually, we can go through. Question 4, part A. If we have a block cipher with an n-bit plaintext input and a k-bit key, and you answered this in your quiz the previous quiz, assume an encrypt operation takes 1 microsecond, decrypt 1 microsecond. What's the worst case time it takes for a brute force attack? This is not breaking double DES, but this is setting up the problem. N-bit key, N-bit plaintext, K-bit key, how long does it take to do a brute force attack? Worst case. Two to the power of K. Microseconds in our case, but 2 to the power of K. There is a K-bit key. We have 2 to the power of K possible keys. Worst case, I need to try all possible keys. On average, half the possible keys, but the worst case, 2 to the power of K. We're going to show that using a double DES or a double encrypt operation on any block cipher, what do you think it's going to take? We said before, doubling the key length went from 2 to the power of 56, 56-bit key, 112-bit key, you would think 2 to the power of 112 operations. 2 to the power of 2K. E.g. for DES, 2 to the power of 56. For double DES, 2 to the power of 12, 112. We're going to show that it doesn't take this amount. This is secure, but it doesn't work. Let's turn on some lights so we can see a bit better. So let's go through the double DES, and then we'll come back to these answers of the other questions. The question is here. An attacker knows two pairs of plaintext ciphertext. Here's the first pair. That is, the attacker knows this plaintext value, 1110, and it knows that when that plaintext is encrypted with a key, that the output is 01111. 011, yeah, 3 ones. It knows that value. It doesn't know the key. It wants to find the key. And it knows another pair of plaintext ciphertext. So we assume the attacker knows these two values. They don't know the key. They want to find the key. The cipher is double A, where A is the table that we have up the top, which I'll go back to in a moment. That is, it's a double cipher that encrypts 2 times with two 2-bit keys. Let's show how the attacker can break that. So the attacker knows these two values. You don't have to copy this down because the exam answers are somewhere on the website. I'll leave on the screen the cipher. What the attacker does in this process is attempts a brute force attack on the first phase of the encryption. That's the double encryption. Take some plain text, get some intermediate value. Let me find my answers so we can do it on the board. The attacker takes, let's choose one of these known pairs, takes the first known pair and takes the plain text and does a brute force attack on it. So we have plain text equal to 1110. That's known to the attacker. Apply a brute force attack on that plain text using the cipher. Our cipher has a 2-bit key, a single operation. Therefore, there are 4 possible values. If we use key 00 and the plain text 1110, then the ciphertext 1110 is here, and the key 00, the ciphertext will be 0010 when we encrypt. That's take some plain text, encrypt with one possible key, get some output. I won't call it C, I'll call it X. It's not the real ciphertext because we need to encrypt again to get the ciphertext. Take the next key and do it again, encrypt the same plain text with a different key, and we get 1000. This is a brute force attack on the 2-bit key. And let's give these some numbers or some subscripts. X, key 1, 2, 3, 4. X, let's call this X1. When we encrypted the plain text, I'll write X1P, x2p, x3p, x4p, where the number 1, 2, 3, 4 refers to the key used, and the p refers to the fact that we've encrypted the known plain text. How many encrypt operations so far? 4 operations from the attacker's perspective. I'll keep track. That is, we've had to encrypt the plain text 4 times. Now what the attacker does is takes the corresponding known ciphertext, 0111, and applies a brute force attack on that and compares the results to what we have here. The idea is that we take some plain text, encrypt with some key, we'll get some intermediate value x. If we take that value of x and encrypt with key k2, we'll get c. The attacker knows P and C. What they're going to do, or what they've done so far, is find, given P, a brute force, try all keys, get 4 different values of x, possible values of x. And now, given C, decrypt with all possible keys, and we'll get 4 possible values of x. And if we've chosen the right key, then the x value, an x value from encrypting should be the same as an x value from decrypting. We should meet in the middle. Let's see it and then explain it a bit more. The attacker now takes our ciphertext value, which is known, and decrypts. The known ciphertext is 0111. What do we get? Have we done this right? Decrypt 0111 using key 1, key 2, what do we get? Decrypt 0111. When we use key 00, the ciphertext is 0111, this value. Therefore, if we take this value using key 00, the plain text should be 0011. I'll call it X1, C. X using key 1, but starting with the ciphertext. Do that for the others. Next one, using key 01, that's this column. Ciphertext is 0111 here. Plain text will be 0110. Decrypt, where are we? 0111 using key 10, 0010. And decrypt 0111 is here with key 11 gives us 0001. So the first step, the attacker tried all possible keys with the known plain text and got 4 potential values of x. x1p, x2p, x4p, these values. And then went from the other direction. Take the known ciphertext, C, and decrypt that with the 4 possible values of the key. And we get these potential values of x. If we take some plain text, P, encrypt with a key and get x, and then take that value of x, encrypt with another key and get C, if this is the plain text and this is the ciphertext, then we should get the same value of x whether we encrypt the plain text with the key or decrypt the ciphertext and get the key. That is, where these values match, that suggests the possible values of the keys. First, where do they match? X1P, X3C, the same value. Does this one appear there? No. This one? Yes. This one? No. We've got two matches here. That indicates that there are two possible correct keys. Only one of them is the correct key. We'll see how to distinguish in a moment. That is, take this plain text, encrypt with 00, you'll get X0010, the middle point. And if we had the ciphertext and decrypt with key 10, we'll get the same value of x. Same with these two values. So potential values of the key are K1 combined with K3 or K3 combined with K1. Remember, our key in this double cipher is two keys of length 2 bits. In the single cipher, the key is 2 bits. In the double cipher, we just choose two different keys, or two keys. So the key is one of these combined with one of these. So far, we've worked it out to be these, any of these two. What do we do next? How do we know which key? Yep. Let's try this key. Assuming K1 is the key, if we encrypt 1110 with K1, we get 0010. If we encrypt 0010 with K3, what do we get? 0010 with K3, 0111. That makes sense. We get the ciphertext that we expect. K1 and K3 take the input plaintext, this, and we'll get the output ciphertext, which is known. K3, take the plaintext, K3, we'll get 0011. Encrypt 0011 with K1. 0011 with K1, we get the same plain ciphertext. Both of them work. Both keys, K1, K3, and K3, K1, give us the known ciphertext given the input known plaintext. So what else can we do to know which of those two is the correct key? Use the second pair. We have another pair, luckily. If we didn't, we'd be out of luck. Let's try. So now we have two potential keys. Let's apply them on the second pair. That is with key K1 and K3. Take plain text 0100, encrypt with K1, and we get 0100, 0100, encrypt with K1, we get 1000. It's not K1, it's encrypted with K1, which is X. Now encrypt this with K3. 1000 with K3, 1101. Is that what we expect? We took this plain text, used the potential key K1 and K3, we get this ciphertext 1101. We know this is the expected ciphertext. What we're doing, we've got two potential key values, two pairs, K1, K3, K3, K1. We need to know which one of those two is the true key. So what we're doing is testing each of those two keys on our second pair of plaintext ciphertext. Encrypt this with K1, we get this output. Encrypt this output with K3, we get this ciphertext, 1101. This matches the known ciphertext, plaintext ciphertext pair. Try the second values. K3 and K1. Take our plaintext 0100, encrypt with K3. 0100, encrypt with K3, and we get 1100. Take that intermediate value, 1100, and encrypt with K1. We get 0101. It doesn't match the known ciphertext value. We know if we use the right key and we encrypt using one of the pairs of known plaintext ciphertext, we will get the right ciphertext. That is, if we have the right key and encrypt this value, we must get this as a ciphertext. When we had tried K1, K3, it worked. We encrypted this value, the output was the known ciphertext. When we tried the different key value, K3, K1, we encrypt the known plaintext, we get a ciphertext value that doesn't match the known ciphertext. That's incorrect. That means that this key is not the true key. It was not the key used to generate this pair. No, this key was a key used to generate this pair and this pair. And that tells us the key. How many operations did it take? We tried all possible keys here, 4 operations. Or in general, with a k-bit key, 2 to the power of k operations. We had a 2-bit key. Then we did it again. We decrypted the ciphertext with all possible keys. Took us 4 operations. In general, 2 to the power of k operations. Because we all try all keys. In some cases, we don't have to even try all of them, but let's look at the worst case. And then, how many did we do here? Well, we tested. We did it 1, 2, and encrypt, and another 2 encrypts. We did another 4 operations here. In general, the number of pairs or number of possible keys that we need to test will be very small. Let's look at the general equation. It takes us 2 to the k plus another 2 to the k plus some few other operations. Ignore these for a moment. Usually it doesn't take many here. In general, it takes 2 to the k plus 2 to the k operations, which is 2 to the k plus 1. It's 2 times 2 to the k, which is 2, we'll come back over here, approximately, because we have a few more here, but when k is large, those few more is very small. It takes us approximately 2 to the power of k plus 1 operations. And in DES, if we expand this up, where k is 56, 2 to the power of 57 operations. That is, single DES takes worst case 2 to the power of 56 operations. We have 2 to the power of 56 possible keys. If that took me 10 hours to break, that's too insecure, it's too short of time. Double DES, we thought initially would take 2 to the power of 112 operations because the length of the key is 112 bits. If 2 to the 56 took 10 hours, then 2 to the power of 112 would take trillions of hours. Too long. But using this attack, this meet in the middle attack, with double DES, it takes us approximately 2 to the power of 57 operations, which is 20 hours. 2 to the power of 57 is 2 times 2 to the power of 56. So double DES is twice as strong as single DES, which is weak. Because DES is weak, and if it takes 10 hours to break, 20 hours is not much more. So it's still considered weak because of this attack. Even though the key length is 112 bits, the attacker only needs approximately 2 to the power of 57 operations to break it. So double DES doesn't provide much more security than single DES. And that's why that's why triple DES has been developed. It does the same approach, and you can attempt the meet in the middle attack, but we don't have one single middle point. With triple DES, we have 3 operations. We have x1 and x2, 2 intermediate values. And therefore, the effective strength is on one of these slides. If we return with a meet in the middle attack, it takes us sorry, where are we? With our meet in the middle attack, it takes us twice as much as single DES, which is not very strong. With triple encryption, I don't have it on the slides. With triple encryption, although we can apply the meet in the middle attack on one part of the operation, then we cannot do it on the entire encryption. And effectively, with triple encryption, or with triple DES, we're up to the 2 to the power of 112. with triple encryption, we have it's strong enough to prevent a brute force attack because we have two places where a meet in the middle attack needs to be performed. Because we can do the attack on triple DES, but we need to do many more. We need to do it multiple times, the attack. That is, if we see that we can do the attack on A, but that doesn't give us the answer. With double DES, we did the attack and found X, the meet in the middle here, but we can attempt that, but we only have the ciphertext and the plaintext. We cannot get to A without going from C to B. So we can get from C to B, we can get from P to A, but we haven't met in the middle. No. So with triple DES, with triple DES there's two variants as well. Triple DES, 3 encrypt operations, but only 2 keys are used in some cases. K1, K2, K1 again. If we use 3 keys, K1, K2, K3, then it's up to 168 bits. And then we'd have 2 to the power of 168. So triple DES has 3 operations, but in some instances we only use 2 different keys. We've doubled the key length and we've doubled the security compared to single DES. Double DES doesn't, we've more than doubled the security. We've doubled the key length and we've produced security which is unbreakable from a brute force attack. With double DES, we double the key length, but it only takes double the effort to break. Double the effort is not much. If I pay $10,000 to break into your account, I might as well pay $20,000 to break into your account. So triple is used and is the standard now. It's not subject to that meet in the middle attack. Okay, that's quite a complex example to go through. Let's summarise the steps that we've seen. With the meet in the middle, we need to know pairs of plaintext ciphertext. So that's an assumption. The attacker needs to know these values. When we have real DES, it may need to know more than just 2 values. It may need to know many possible values. If we know different values of plaintext ciphertext, then we take our known plaintext, do a brute force attack on that to get potential values of X, the middle point. Then we take the corresponding known ciphertext and work backwards. Do a brute force attack on that and get potential values of X. And when we apply from both directions, if the values of X match, are the same in the middle, then that suggests what the key values are. K1 that produce the value of X, X1P, that matches a value of X going in the opposite direction, X3C, then since these 2 values match, potential key is K1, K3. And there's another potential key. We may have many potential keys. And the more we have, the more known plaintext ciphertext pairs are needed. Sometimes we just need 1 known pair. Sometimes we need more than 1. And we apply them and we just check the potential keys. Of these 2, we check them both on the next pair. The one that worked is the key. Eventually you can filter out the ones that don't work using multiple plaintext ciphertext pairs. You'll see in past exams there's been such a question, and in fact there was a question in one of the quizzes one year. So have a look in that. It's interesting to see how it works. It turns out it's an easy way to break what we would originally think is a strong cipher. That describes the steps. and therefore we get triple DES, and there are variations of triple DES. We have 3 steps. That's the triple. There are variations in how to apply it, that we encrypt, decrypt, and encrypt, as opposed to encrypt, 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 just to be compatible with some previous implementations. And there are variations in how we use the key. Do we use 2 keys of 56 bits and effectively get a 112-bit key, K1, K2, and use K1 again? Or do we use 3 separate keys and give us a length of 168 bits? Again, the longer key the better, but 112 bits should be enough. A smaller key to distribute. The last cipher we just mentioned here, and it's a widespread cipher now, is the Advanced Encryption Standard. Because DES was considered weak from the key length perspective, then the US government tried to develop a new cipher, and that eventually became the Advanced Encryption Standard. It uses a block size of 128 bits, although it allows other block sizes. DES was 64 bits. It allows different key sizes from 128 bits up to 256 bits. They should be long enough to prevent a brute force attack. 56 bits is not long enough. 112 should be long enough. Greater than that is fine for future purposes. It has varying number of rounds. It uses S boxes, XOR, and some other mathematics to do the operations. We're not going to look at it in any detail. There's a simplified version, simplified AES, and in the textbook and even online there are some examples of that if you want to see how it works. But it's widely used nowadays, AES, and generally considered secure. And triple DES is also widely used, especially in government applications. And there are other block ciphers. We've just mentioned DES, triple DES, AES. There are others, but not as popular in some cases. Have been developed by different people and have different advantages and disadvantages. There's some of them listed there. You'll find many online. Finishes on block ciphers and DES, but doesn't finish our lecture. Yeah?
Can you explain the homework?
Yes. In a minute. I'll explain the homework in a moment. First, a very short example to motivate what we're going to do next, but we won't start the next topic. What we've dealt with block ciphers, we saw DES operates on 64 bits. AES 128 bits. But the data that we want to encrypt is almost always larger than that. I want to encrypt a file, then how do I encrypt a file which is 1 megabyte? Well, the approach is to break the file into 64-bit blocks and encrypt each block one at a time. That is, if I have 640 bits, divide it into 10 blocks of 64 bits. Encrypt the first 64 bits with my key, encrypt the next 64 bits with the same key, and so on, the 10 blocks, and combine those 10 ciphertext values together. That's a way to encrypt large files, larger than 64 bits, with block ciphers. What's the problem with that? What's the problem with encrypting, say, a large 1 megabyte file, breaking the plain text into blocks, encrypting each block together, Each block. It doesn't, I mean, we cannot avoid encrypting all of it, so no, it doesn't take too long. No, it works. It works fine. What's the security problem?
When the attacker tries to encrypt it, it can like separate the ciphertext into a chunk of blocks, then encrypt it.
So the attacker has the ciphertext. They know it's just made up of blocks of plain text. The problem is that we get repetitions again. Because if I encrypt one block of 64 bits, I've got a very large file, 1 gigabyte. I take 64 bits at the start, encrypt with my key, I'll get a ciphertext value. If somewhere else in the file I've got the same 64 bits, I encrypt with the same key, I'll get the same ciphertext value. So if we have repetitions in the input plaintext file of 64 bits, we'll get repetitions in the output ciphertext. And whenever there's repetitions or structure in the ciphertext, the life becomes easier for the attacker. Our next topic is about how to avoid that problem by using different approaches for combining the ciphertext and plaintext, different modes of operation. But we're not going to start that lecture yet. We're going to talk about the homework. The homework requires you to encrypt a message with DES. And I suggest you use, or I require you to use the OpenSSL package. OpenSSL is a free package for doing encryption. It's a library as well as a standalone application. A library means that many of the ciphers are implemented, and if you write your own application, you can use that library. You don't have to implement DES or AES. You use the library of functions that they provide. Yep. The message needs to be a message that I can understand. And there's a limit on the size only so that I don't have to read long emails or read the message as long. So, in fact, it can be any size so long as it's reasonably large. So what you need to do is encrypt some message that you choose. It needs to be a message I can understand. It doesn't need to mean anything. It could be a picture. So it doesn't have to be text. It needs to be a message or some information that I can understand. And you need to encrypt it with DES. And you use OpenSSL software to do that. And OpenSSL is available in most operating systems. It's installed by default in Linux operating systems, including the IT server. If you log into the IT server and type OpenSSL, it will work. So that's the easiest way if you don't have it currently installed on your computer. That's right. It should, most Linux distributions, it would be installed already. Mac OS, is it installed already? It's installed on Mac as well. They may be different versions, but I'm 99% sure the old versions will still work for the task that you need to do. Windows, it's not installed. You can get a copy, but it may be easy, you can get it for free, but it may be easy to just log into the IT server. It's just for a small task. If you use the IT server, then the message that you want to send me needs to be on the IT server. You either create it on there using some text editor, or you copy a file from somewhere, or you upload it to the IT server. That's for you to work out, whichever you choose. You have your message. You use OpenSSL on the command line. So basically you read this page, not all of it, and it will tell you the commands that you need to use, the options to use. Let's look at the question. On the website. just log in first. The homework. So there are some conditions and you must follow them, because otherwise I will not decrypt correctly. When I receive your ciphertext, I'm going to decrypt. If I get a message I can understand, you pass. If it produces an error, you fail. So read the instructions, especially encrypt the message using DES, using cipher block chaining, although we haven't described that. In the lecture tomorrow we will. You need to select the key. You don't use a password. OpenSSL gives you the chance of using a password. Don't do that. Select the key. Do not use assault, although we haven't explained the purpose of assault. We don't use it in this case. And although the software may ask for an initialization vector, it's not relevant for DES. So you use a value of 0 if it asks for it. You encrypt your message, you'll get some ciphertext, but that ciphertext is a sequence of bits. If you send it in an email, it may not be transferred correctly. If you put it on print it on the screen, it will ruin up your screen because it shows strange characters. You may not be able to copy them. So what you need to do is take your ciphertext and convert it into a format that can be printed on the screen and sent in an email. That format, or that conversion, is performed using base 64. It simply converts the binary values into characters which can be displayed on the screen and can be sent in an email. Lucky for you, OpenSSL has an option that turns on base 64 formatting. Just find the option. And send me an email with your information. You need to send me your key, because I need to decrypt it. Sorry? If you use a picture, try. And you can test that you cannot test all the options, but you can test that it's worked by decrypting. But you need to make sure you get the right options. Anything. Don't make it too small. Not less than 1 kilobyte. Don't make it too large because you need to send me in an email and I don't want 40, 10 megabyte files. Don't tell everyone your message, it's a secret. So you choose a message. So don't tell everyone else your message. Try. You can send an image, but I suggest sending text, only because it will be easier for me. Send text, but any characters. Any other questions? I haven't checked the ones I've received. I've received some. How am I going to know it's correct? The message needs to make sense to most people. A random set of characters would not be a good message. So, some text, preferably. Any other questions? So that people work on their own and attempt it. So that one person doesn't find the answer and give it to everyone else.